In this example, we take a look at calculating confidence intervals. It's not necessary to draw an interval plot every time we want to construct a confidence interval estimate. Starting with the point estimate in the center, we can numerically calculate confidence intervals using the formula point estimate plus or minus a margin of error. When we subtract the point estimate minus the margin of error, that gives us our lower limit. And when we add the point estimate plus the margin of error, that gives us our upper limit. So when we construct our margin of error, we're going to make use of what we already know from normal distributions, that approximately 68% of the observations fall within one standard deviation, sigma, of the center. Approximately 95% of the observations fall within two standard deviations, sigma, of the center. And approximately 99.7% of the observations fall within three standard deviations, or 3 sigma, of the center. The relationships that hold for the standard deviations, we're going to have the same estimates and relationships hold for the standard error for normal distribution. Remember, the standard error is the standard deviation of a sampling estimate. Professors at Los Medanos College would like to estimate the proportion of statistics students at California community colleges who are also taking English. As a project, they surveyed 320 students currently enrolled in statistics. Here's the data. You can see students were asked, are you also enrolled in English class at LMC or another school? 320 students total were surveyed. 207 said yes, they were enrolled in an English class, and 113 said no, they were not. So remember, these are students who are in statistics, so we're asking if, in addition to statistics, are they also in English or not. So we want to calculate a point estimate. It's going to be a sample proportion, because we're working with categorical data, for the number of yes responses, and we're going to round our results to 4 decimal places. So our sample proportion is P with that hat on top, or the caret symbol above 6 on the keyboard. If you're having a hard time typing it, you could just type the words P hat or P and then put the caret above 6 after it. Sometimes it's hard to get the accent above the letter, so however you want to type it is fine. You could also just call it sample proportion. So that equals 207 who said yes out of 320 total surveyed. As a decimal, if we divide and round to 4 places, we get 0.6469, or about 64.69%, if we want to think about this as a percent. So this is a sample proportion from our survey data of statistics students who are also taking English. Since the population proportion P is not known, we are going to rely on the sample proportion P hat as our estimator. So we are going to use this value to check that the normal conditions n times P hat are at least 10 and n times 1 minus P hat are at least 10. So here we're using the P hat, not the population proportion, because that population proportion, there's no estimate or given value to us. So n times P hat, well, that's 320 times 207 over 320. Well, we know those 320s would just cancel, so this is just 207. So that's exactly the people that said yes. And then n times 1 minus P, there should be a hat on there. I left the hat out when I wrote that. Equals 320 times 1 minus 207 out of 320, or 320 times 113 out of 320, which is 113, which is just our count of the no's. So we have more than 10 in each group, so we can use a normal approximation. And what that means when we say we can use a normal approximation is that we can assume the graph of this data for a large survey would be bell-shaped. And then notice here that these rounded calculations, n times P hat and n times 1 minus P hat, match just the count of yes and no responses in the survey. So when we're working with 2-answer survey questions, it's sufficient to verify that you have at least 10 responses for each answer. So if you've got a table with your data already, you can just check to see, are there at least 10 folks in each group that we're counting up here? So it's not necessary to go through these calculations. If you can verify from the table, you could write a sentence to say, we verify there are at least 10 responses in each group. So we have enough data to use this normal approximation. All right, question C. The values of population parameters are often unknown, as in this case, making it impossible to compute the standard error of a statistic. When this occurs, that we use the estimated standard error. Just like earlier that we used p hat, the sample proportion, instead of the proportion, we do the same thing for the estimated standard error. So you can see here our formula looks almost the same as the standard error formula, except we have the p with the hat in it. So we're going to calculate the estimated standard error. I'm just going to call it SE again and know that it's using estimated data. So I do 0.6469 multiplied by 1 minus 0.6469, all divided by 320, because 320 is our sample size, and then we're going to square root at the end. So I do the subtraction first, since that's in parentheses, and then I multiply, divide, and square root, and I get for our estimated standard error 0.0267. So very often in real life, we don't know the population proportion, so we work entirely with the sample data. So all of our calculations are estimated standard errors. All right, in this investigation, our goal is to estimate a population proportion. So we're trying to help the professors at LMC predict how many students who are on statistics are also taking English. Professors at LMC selected a random sample from the population, and we are using the sample proportion as an estimate. Of course, random samples vary, so we want to include a statement about the amount of error that may be present. Because sample proportions vary in a predictable way, we can also make a probability statement about how confident we are in the process we use to estimate the population proportion. Our goal is to construct an interval that we are reasonably confident contains the population proportion. In the previous question that we looked at, we used the fact that most sample proportions, usually about 95% of sample proportions, fall within 2 standard errors of the center. So we know that from the normal distribution breakdown, the 68, 95, 99.7% rule that we've seen. So using this fact, we construct an interval that we are 95% confident contains a population proportion. We're going to construct that interval by starting with the sample proportion, and then we're going to add and subtract 2 standard errors. So we're going to have 0.6469 plus or minus 2 times 0.0267, because that's our standard error. So this is going to be 0.6469 plus or minus 0.0534 after we do that multiplication. So we subtract to find the lower bound, and we add to find the upper bound. StatCrunch calls this lower limit and upper limit. I use those terms bound and limit interchangeably. It does not matter if you call it a lower bound or lower limit. Same idea. So the lower bound or the lower limit of the confidence interval is 0.5935 or 59.35%. And the upper bound of the confidence interval is 0.7003 or 70.03%. So this is the range that we think the real population proportion of statistics students who are also in English lies. So here is how we can interpret the interval, highlighted here in my purple highlighter. We could say we are 95% confident that between 59.35% and 70.03% of all California community college students enrolled in a statistics course are also enrolled in an English course. So there are several different ways we can say it. What's important here is that 95% tells you how sure I am in these calculations, or how sure we are that we captured the true population value. You can report the population value as a percent range or as a proportion range in decimal form or fractional form. Either way is okay. You want to make sure you're predicting about the whole population. So notice I underlined here that I'm predicting about all of the California community college students. And then you want to explain what you're predicting. So in this case, we're predicting those who are enrolled in a statistics course and are also enrolled in an English course. Down here, highlighted in yellow, is another way that we can interpret it. So there's a variety of ways that you can explain as long as you're conveying the right concepts. So we could say the confidence level is the success rate of the method that produces the interval. To say that we are 95% confident, the unknown proportion lies between 0.5935 and 0.7003 is shorthand for we got these numbers using a method that gives correct results 95% of the time. So we're conveying the same idea. Instead of percents, we've presented the range of values as a proportion in decimal form. And we're explaining that 95% is how sure we are that we captured that true population value. So users can choose a confidence level. Usually we like to choose 90% or higher because we typically want to be quite sure of our conclusions. So when we are interpreting the confidence interval, there are 3 key elements to include. You want to include your percent confidence in your calculation. That would be how sure you are that you are capturing the parameter in your interval. Remember, the parameter is the value about the population. You want to be clear that you are making a prediction for the parameter. That's the true population value. So remember that you already know all of the sample data, so you would never need to make a prediction about the sample data. You're always predicting for the larger group that you don't have data from. And the range of possible values from the lower bound to the upper bound of the interval needs to be given. So we're going to use that standard error we calculated to estimate the 68% confidence interval for the proportion of statistics students who are also taking English, and then we're going to interpret that meaning with a sentence. So the 68% confidence corresponds with one standard error in the margin of error, and for short, I'm going to call the margin of error the MOE. So we're going to do 0.6469 plus or minus 0.0267 because that is one standard error from our standard error formula we did earlier. So our lower bound, or you could call it the lower limit, when we subtract is 0.6202. And the upper bound when we add is 0.6736. So now we need to interpret it, making sure we get these 3 key elements from above in our interpretation. So here I've said, and I'm sorry, it's a little hard to read my handwriting, we are 68% sure, that says sure, you could also say we are 68% certain, that we have captured the true population proportion of all California community college students in statistics who are also in English in the interval 0.6202 to 0.6736. So here I explained that I was 68% sure. I could say I'm 68% confident, or I used a method that works 68% of the time. I'm saying that I think we've captured that true population value for all the California community college students, and then I've given my range in decimal form. All right, now in question E, we want to use the standard error to estimate the 99.7% confidence interval for the proportion of statistics students who are also taking English. And then we're going to interpret again with a sentence. So we know from the normal distribution that 99.7% confidence corresponds with 3 standard errors in the MOE, the margin of error. We know we can use a normal distribution because we checked that we had at least 10 in each answer category, the yeses and the nos. That check is always the first thing you have to do before jumping into these kind of calculations. So we are going to calculate 0.6469 plus or minus 3 times our standard error, the 0.0267. So I multiply 3 times the standard error first. So now my calculation is going to be 0.6469 plus or minus 0.0801. So we subtract to find the lower bound, or the lower limit. So that is 0.5668. And then we add to find the upper bound, and that is 0.727. So notice the lower bound goes lower than in the earlier interval that was only 68% confident. And the upper bound goes higher than the earlier interval that was only 68% confident. And that's because here we're using 3 standard errors in our margin of error, so we're going to have a wider interval. So we can report we are 99.7% confident that between 56.68% to 72.7% of all California community college students in statistics are also in English class. So here I've used a percent instead of a decimal to give my range. It's up to you whether you use decimal or percent. And I've made sure that I'm predicting with the whole population, in this case, all California community college students. So question F asks us to think about which was the widest confidence interval, the 68%, the 95% that was calculated for us, or the 99.7%. So we can see, looking from the lower bound to the upper bound, and we can subtract if we need to check, that the widest interval is the 99.7% confidence interval. Since we are more confident that we captured the population proportion, we need to have a wider range of values. So in the 99.7% confidence interval, we were using 3 standard errors. So our margin of error that we were adding and subtracting was the 0.0801. So we went lower for our lower bound and higher for our upper bound because we had to be more sure that we had the true population proportion. Now you can imagine you could go so wide that your values aren't particularly helpful. Imagine if we went to like 10 standard errors, we'd be really sure, but our values would be something like, 10% to 90%, which wouldn't be giving us a whole lot of information we couldn't have guessed on our own. So we want to try to balance the width of the interval with the range of the values. So in this case, 3 standard errors gives us a range from 56.68% to 72.7%. So that's still a narrow enough range to be helpful for us.